Problem sheet 4, question 5. In an A&E department that is open for 24 hours, patients arrive according to a Poisson process at rate 35 per hour. Of these, a seventh are categorised as triage category 1, 2 sevenths are categorised as triage category 2, and 4 sevenths are categorised as triage category 3. Patients wait to be seen by one of the 18 doctors on duty at the A&E, and they are seen by a doctor according to priorities. Triage 1 patients have priority over triage 2 patients, who in turn have priority over triage 3 patients. The time it takes to see each patient depends on their triage category. Triage 3 patients are given a 15-minute appointment. Triage 2 patients' time with the doctor is uniformly distributed between 15 and 25 minutes, and Triage 1 patients' time with the doctor is uniformly distributed between 20 and 90 minutes. What is the average waiting time for patients for each triage category? First, we will consider the conceptual model. So a few things to highlight here. First is that the A&E department is open for 24 hours. So it does not have a defined start and end date. It just runs constantly for 24 hours. Therefore, when we are talking about the average waiting time, what we are talking about is the steady state average waiting time. So that will come into play when we implement the model. The other thing here is that we only have one service centre and one queue. So we could draw this as one service centre and one queue. There are 18 servers. That's a bit too much to draw. So we're just going to put this in here and we will say that the number of servers is equal to 18. We have 3 streams of patients arriving. So we have 3 streams of patients arriving in, and I've staggered those arrows here just to indicate that some have priority over others. Triage 1 patients have the highest priority, so they will arrive with lambda 1 and arrival rate lambda 1. Triage patients 2 have the next priority, they will arrive with rate lambda 2, and finally triage category 3 patients will arrive with arrival rate lambda 3. Now, what are those lambda 1, 2 and 3s? Well, we know that the overall arrival of the patients is Poisson process with the rate 35. And due to Poisson thinning, when we know that a seventh of those are triage category 1, we know that lambda 1 will be equal to 35 times by a seventh. So in this case, lambda 1 is equal to 5. Lambda 2, due to Poisson thinning, they're going to arrive with rate 35 times 2 over 7. And lambda 3, again due to Poisson thinning, they're going to arrive with rate 35 times 4 over 7. So we can write these in. Finally, those servers, those 18 servers, will operate at a given service rate, mu, which depends on the triage category. So we have mu1, mu2 and mu3 here. Now the service time distribution isn't necessarily exponential here. In fact, it's never exponential. For triage category 3, patients spend a fixed time of 15 minutes as a deterministic service time distribution, which still would have a rate of 4 per hour. 15 minutes times 4 is an hour. For triage category 2, they are uniformly distributed between 15 and 25 minutes. So that would be on average 3 per hour. And for triage category 3, they're going to be uniformly distributed between 20 and 90 minutes. So that's just under 1 per hour. So this would be our conceptual model. So now let's think about the implementation. We'll do this using Q. So first let's import the Q library. And as always, we will create a network object that represents our conceptual model. The first argument of this function is the arrival distributions. Now we only have one service center here, so our parameters will be lists of length 1, but we do have 3 different types of customer arriving. There's 3 different classes of customer. So how do we deal with that? We deal with that in Q using dictionaries. where the keys are strings representing the names of the customer class. So we can name them whatever we want. In this case, triage 1, 2 and 3. And for customers of class triage 1, we can then do our usual list of parameters for each service centre. There's only one service centre here, so it'll be a list of one thing. The arrival distribution for customers of triage category 1 is going to be Poisson arrivals with arrival rate lambda equals to 5 per hour. However, remember we've defined our arrival rates with a time unit of hours, but all our service rates were defined in minutes, slots of 15 minutes, uniformly distributed between 15 and 25 minutes and so on. So it's important to keep all our time units the same. So let's choose minutes as our time unit. So therefore our arrival rate for patients of triage category 1 will be 5/60 per minute rather than 5 per hour. Similarly for triage 2, this will be 10/60 rather than 10. The second argument in this function that creates our network will be the service distributions. Again, this works similarly to what we did before, where we'll define a dictionary with keys corresponding to the customer class names and values corresponding to those parameter lists. Customers of triage category 1 have service time uniformly distributed between 20 and 90 minutes. Customers of triage category 2 have service time uniformly distributed between 15 and 25 minutes. And customers of class triage 3 have fixed length service times, that is a deterministic service distribution with value 15. We now have to define the number of servers. There are 18 servers. Notice number of servers isn't split between different classes because all customer classes use the same pool of 18 servers. There is no need to define routing here because there is only one service center, but the one thing we have missed here are these staggered arrivals, which represent that some customer classes have priority over other customer classes. So we can represent that with the keyword argument priority classes, and this will take a dictionary that will map customer class names to their relative position in the priority hierarchy, with 0 being the most prioritized, then 1, then 2, then 3, and so on. So this network object completely defines our system and our conceptual model. Now recall we said that this was a steady state model, so we have no defined start and end times, and therefore what we would like to do is run this for a very long time with some sort of warm-up time. So let's say we want our warm-up time to be 1 day. We want to run this simulation for a whole day before collecting any results. A day in minutes is 24 times 60. And say we want to run the full simulation for a month, that is 30 days. That many minutes. Then we can set a seed to ensure reproducibility, create our simulation object, the simulation engine, that is created out of our network object, so it understands the system that we are modeling. You can simulate this until a certain amount of time has passed. And the amount of time we want to pass is going to be the warm-up time plus the amount of time we are simulating this for. Once that has run, we want to collect all our records. and then it would be good to filter out all the records that were collected during the warm-up time. So anyone who arrived before the warm-up time has ended, we will filter them out. We don't want those. So we will create a new list of all the records are in all records, such that if r.arrival date is greater than the warm-up. So we can look at that list of records, which is something quite unwieldy. So let's have a look at just one particular record in there. And we can have a look at, in that one particular record, what were their waiting time. So we know at least one person waited 0.159 minutes. That particular record corresponded to someone of triage category 2. Our question was asking us, what is the average waiting time for patients in each triage category? So we can use these attributes of the data records to find that. So what is a list of all the waiting times for people in triage category 1? So that will be the record.waiting time for record in our filtered records if that record's customer class is equal to triage category 1. We can do the same thing then for each triage category. And finally, we can see the list of all the waiting times of people in triage category 1. So we'll be able to find the average by summing over this list and dividing by the size of that list. So the average waiting time for customers in triage category 1 is 0.172. The average waiting time for customers in triage category 2 is 0.2501 minutes. And the average waiting time for customers in triage category 3 is 0.671 minutes. We see that the more prioritized customers, triage category 1, have a lower average waiting time than the others. And that is exactly what we would expect in a situation like this. So that's a little bit of a sense check for us as well.